The universe is 93 billion light-years across. You are made of stardust. But one thing is certain, you are not the center of it. Imagine a black hole so massive light would take 100,000 years to cross it. Now imagine it defying the laws of physics we thought were unbreakable. Scientists call it the information paradox, a mystery that haunts quantum mechanics and general relativity alike. This isn't fiction. It's the unresolved clash between Einstein's relativity and Hawking's quantum theories, tested by black holes like Sagittarius A and M87. Number 1. The black hole that swallows time. At the Milky Way's center lies Sagittarius A, a supermassive black hole that warps space-time so violently. Time itself stretches and tears. Near its event horizon, time dilation becomes extreme. 1 hour near the black hole equals years for an outside observer. It's like watching a clock melt into the void. Reinhard Genzel and Andrea Gheze's Nobel-winning work confirmed its existence. But the question remains, what happens to information swallowed by it? Does it vanish, or does it haunt the universe forever? Number 2. The Event Horizon Telescope's nightmare. In 2019, the Event Horizon Telescope captured the first image of M87, a black hole 55 million light-years away. But its shadow wasn't what they expected. The image showed a ring of light, general relativity's prediction, but the absence of a visible singularity left physicists scrambling. What if the singularity isn't a point, but a quantum foam? Sheperd Doeleman's team celebrated, but the data hinted at something deeper, a breakdown of classical models where quantum effects dominate. Number 3. Gravitational waves that break general relativity. In 2015, LIGO detected gravitational waves from 2 black holes merging. In 2019, the Event Horizon Telescope captured the first image of M87, a black hole 55 million light-years away. But its shadow wasn't what they expected. The image showed a ring of light, general relativity's prediction, but the absence of a visible singularity left physicists scrambling. What if the singularity isn't a point, but a quantum foam? Sheperd Doeleman's team celebrated. But the data hinted at something deeper, a breakdown of classical models where quantum effects dominate. The shadow was perfect, but the darkness at the center was too smooth. According to Einstein, the singularity should be a point of infinite density, yet the image showed nothing. Was it a flaw in the telescope, a limitation of our models? Or was the singularity not a point, but a smeared-out quantum structure? Theorists like Kip Thorne argued that the ring of light was a triumph for relativity, but the void at the center defied explanation. Could the singularity be a quantum bridge to another universe? The data didn't answer, but it screamed for new physics. Every pixel in that image was a question mark. The universe had shown its face, but the face was incomplete. What if the laws of physics we knew were just the surface of something far stranger? The black hole wasn't breaking physics, it was exposing its limits. And that, scientists realized, was the most terrifying part of all. The collaboration involved over 300 scientists across 60 institutions, working for years to capture that single image. Yet, even as they celebrated, the void at the center of M87 remained an enigma. It was as if the universe had whispered a riddle, and the answer lay beyond the reach of current physics. The singularity's absence was a cosmic taunt, challenging every theory we had built to understand the fabric of reality. In the end, the image was both a confirmation and a warning. Our understanding of the universe is still in its infancy, and the true nature of black holes may require a revolution in physics that we haven't even begun to imagine. The absence of the singularity suggests that our models of space-time might be incomplete, and that the extreme conditions near a black hole could be governed by quantum gravity, a theory that remains one of the greatest unsolved mysteries in science. In 2015, LIGO detected gravitational waves from 2 black holes merging. It was a triumph for Einstein. But then came the anomaly. The waves' frequency and amplitude matched predictions, but the merger's final moments suggested energy loss unaccounted for by general relativity. It's as if the black holes remembered their past. Kip Thorne's models predicted a perfect ringdown, a clean decay of the merged black hole into a stable state. Yet the data showed irregularities, like a heartbeat out of sync. The signal's tail was too long, too messy. Physicists scrambled. Was it a flaw in the detector, a glitch in the data, or something deeper? The LIGO team ran simulations, cross-checked with Virgo, and found the same strange echo. The energy discrepancy was minuscule, less than 1%, but enough to unsettle the most confident theorists. If general relativity had failed, even slightly, it would have shattered the century-old framework. But the anomaly wasn't a contradiction, it was a whisper. A hint that quantum effects, usually invisible, might leave fingerprints in the most extreme cosmic collisions. Theorists like Kip Thorne and Richard Price debated furiously. Could gravity itself be a quantum phenomenon, revealing its true nature only in the final moments of a black hole's life? The data didn't confirm it, but it screamed for new physics. Every oscillation in that gravitational wave was a question. The universe had spoken, and for the first time, it wasn't in the language of Einstein. It was in the language of something older, something deeper, something we've only begun to listen for. In 1974, Stephen Hawking proposed that black holes aren't the eternal prisons we once thought. They emit radiation, slowly leaking energy until they vanish entirely. This Hawking radiation was a revelation, but it birthed a nightmare. If a black hole evaporates, what happens to the information it devoured? Quantum mechanics says information can't be destroyed, but general relativity suggests it vanishes into the singularity. The paradox is a knife between two pillars of physics. Leonard Susskind, a physicist who once debated Hawking over a bet, argued that information isn't lost, it's scrambled, encoded on the event horizon like a hologram. But how? If a black hole's radiation carries no trace of its past, the universe forgets. It's as if you dropped a book into a fire, and the ashes said, "We don't remember the words." Theorists like Juan Maldacena and Leonard Susskind proposed the holographic principle, suggesting the universe's information is stored on its edges like a 2D projection. But no experiment has confirmed this. The paradox isn't just academic, it's existential. If information is erased, reality itself becomes inconsistent. Theorists have proposed firewalls, quantum entanglement, and even the idea that black holes are portals to other universes. Yet, every solution creates new problems. The absence of Hawking radiation in observations means we're still blind. We've mapped galaxies, detected gravitational waves, and imaged black holes. But the most fundamental question remains, does the universe have memory, or is it a machine that forgets? The information paradox isn't just a riddle, it's a mirror, reflecting the limits of our understanding. And as we stare into the abyss of a black hole, we're forced to ask, if the universe can't remember, can we? The search for quantum gravity is a war between two titans, string theory and loop quantum gravity. String theory posits that all particles are vibrations on tiny one-dimensional strings existing in 10 or 11 dimensions. These extra dimensions curled up like origami might explain why gravity is so weak compared to other forces. But no experiment has glimpsed them. Loop quantum gravity, by contrast, attempts to quantize spacetime itself, treating it as a network of discrete nodes, like a cosmic spiderweb. Both models predict black holes aren't singularities but quantum bridges, portals to other universes or regions of space-time. But how? If a black hole's singularity is a quantum foam, could it be a gateway? Theorists like Carlo Rovelli argue that space isn't continuous but granular, with a minimum length scale called the Planck length, certain. If true, falling into a black hole might not end in oblivion, but in a bounce where space-time rebounds like a compressed spring. This idea, rooted in loop quantum gravity, suggests black holes aren't endpoints but transitions. But how to test it? The James Webb Space Telescope scans for anomalies in gamma-ray bursts, hoping to find echoes of quantum gravity in the aftermath of mergers. Meanwhile, the LHC accelerates particles to near-light speeds, searching for micro-black holes that might reveal extra dimensions. No luck yet. Theorists like Lee Smolin warn that without experimental data, these models remain mathematical fantasies. But what if they're right? If black holes are quantum bridges, they could explain dark matter, missing mass that doesn't emit light, or the multiverse, where our universe is a bubble in a foam of colliding realities. The problem? We're blind. No instrument can probe the Planck scale, so we're stuck between two extremes, models that predict the impossible and data that confirms the mundane. The universe whispers secrets in a language we're still learning. And as we stare into the abyss of a black hole, we're forced to ask, are we looking at the edge of reality or the edge of our understanding?